Okay, welcome. We're going to discuss some properties of integration. The very end of the last thing we learned, was that an integral is the limit of a Riemann sum. And we began, very quickly, we began with a conversation of, suppose you have some velocity versus time curve, and you want to know the total distance traveled. Here's A and here's B, and these are times, and I want to know the distance that was traveled on this interval. Well, what you can do, even if you have some function where the velocity is changing at every moment, you can estimate the velocity, you can estimate rather the change in position or the distance traveled by splitting it up into a bunch of small rectangles and letting each of these rectangles represent the distance traveled on that small interval, assuming on that small interval that your velocity is constant. And you're multiplying a tiny interval of time by the height of the rectangle, which is the velocity that you were going on during that time interval. So if you go at a certain rate times a certain unit of time, then that's the distance traveled during that small unit of time. And this approximation with rectangles is not perfect, but if you use more and more rectangles, it will get more and more perfect. If you let the number of rectangles go to infinity, you seem to get the exact area under this curve. In fact, we basically define the area under this curve to be whatever comes out of this infinite process of approximating it with rectangles. Then we extended this further by talking about how you don't need to necessarily choose the left endpoint or the right endpoint, or the midpoint or any other process. As long as you partition your interval in some kind of reasonable way, then you may have intervals even with possibly unequal widths, and you can choose any point whatsoever that you want to within that subinterval, and it all doesn't matter in the end, because as long as you let the number of rectangles go to infinity, the point that you choose inside each subinterval is irrelevant. Okay, so the end result of all of this was this concept of a Riemann sum, and a Riemann sum says that you partition the interval up into subintervals, and on each subinterval you choose a sample point. You plug that sample point, let's call this x sub I star, into the function, and whatever the height of the function is at the sample point on the ith subinterval, times whatever the width of that ith subinterval is, this gives you the area, intuitively speaking, of that rectangle. And if you add these all up, you get this thing called a Riemann sum. And if you take the limit as n goes to infinity, then we call this the integral from a to b of the function. Okay, this was all just last video. Maybe we didn't need this review, maybe we did. What I would like to do now is to lean heavily on this definition and common sense and physical interpretation to investigate certain properties of integrals. Okay, so we're going to go through, we're going to try to come out of this conversation with some properties and also sort of a deep understanding of what integration is and how the formal definition supports our intuition. So, alright, long-winded ramble build-up, let's begin. Suppose I want to take the integral from a to b of some constant function. So c is just a constant. Well, what is this? I claim there are three ways of approaching this problem. The first way is to just think visually and geometrically. What is the integral from a to b of a constant function c? Well, if we interpret the integral as the area, and isn't that what it is, then we can simply graph from a to b some constant function c, which is of a certain height, c. And then the integral becomes simply the area of this rectangle. And okay, I can calculate the area of this rectangle using basic geometry knowledge, and so this is going to be c times b minus a. So in fact, that is kind of a theorem, that the integral of a constant function is just that constant times the width of the interval, or the difference between the upper limit of integration and the lower limit of integration. Alright, and it seems maybe there's nothing more to be said about this, but I would like to see how our formal definition of the integral as a limit of a Riemann sum supports this. So what can we do? I'm going to sort of draw maybe a new picture that's a little bit bigger. So if this is A and this is B over here, well, what am I really supposed to do when calculating this integral? So I'll sort of now try to just very naively try to redo the problem without any kind of geometric intuition or understanding, but just using the definition that we ended last class with. Well, okay, here's a function on the interval a, b. What am I supposed to do again in order to calculate this integral? Well, I'm supposed to split the interval up into subintervals. How many subintervals should I use? Well, I'll just use n. I'm going to eventually let n go to infinity. And since I don't seem to have any reason not to, I will use equal width subintervals. So if I use equal width subintervals, then delta x is b minus a over n. So take the total width, b minus a, and divide by the number of subintervals. That's the width of each subinterval. And so, okay, that's a. Oh, I'm going to use rm because, why not? That seems like the best method. So this first one will be a plus delta x, this first x value, where I'm going to look at the height. The next one will be a plus 2 delta x. The next one will be a plus 3 delta x, etc. All the way over to the last one, which will be a plus n delta x. And if you multiply delta x by, so this is because I've moved over n times, if you multiply n delta x, if you multiply delta x by n, you get b minus a, and a plus b minus a is b, so it all checks out. What's the point of all this? The point of all this is that I can write and I can just lean directly on the definition of the integral. What is the integral? It's supposedly the limit as n goes to infinity of some Riemann sum. What Riemann sum? The sum from I equals 1 to n of, what am I supposed to be adding up? Well, I'm supposed to be taking the interval from a to b, splitting it up into subintervals, on every subinterval choosing a sample point. I choose, in this particular case, the right subinterval, and so this is going to be f of a plus, and by the time I'm on the ith subinterval, how many times have I shifted right? I times. So this is going to be b minus a over ni times the width of that subinterval, which is just delta x. So maybe I'll just write b minus a over n. Okay. This is seemingly very abstract, but it's all just correct, right? This is my sample point on the ith subinterval. I plug it into the function. I get a y value. I multiply by the width of that subinterval. That gives me this sort of product, which I interpret as the area. I add them all up. I take the limit as n goes to infinity. All right, well, having done all that, I hope we agree that this is a little bit silly, because what is f of a plus b minus a over n times I? Well, it's just a constant function, so f of anything is just going to be c. So this becomes the limit as n goes to infinity of the sum from I equals 1 to n of, well, just c times b minus a over n. Alright, now what? Well, I have this summation, but in fact, c is a constant, b is a constant, a is a constant, and even n, the number of subintervals, is a constant inside the summation. And the only thing that's changing is I, but in fact the function for what I'm adding doesn't even depend on I, which is just another way of saying that all of this can be just pulled directly out of the summation. And so I'm really taking the limit as n goes to infinity of c times b minus a over n times the sum from I equals 1 to n of just 1. Okay, and what happens when you add 1 plus 1 plus 1 plus 1 n times? Well, in fact, you just get n. And so this is the limit as n goes to infinity of c times b minus a over n times n. Okay, well, the n's cancel, and that's just a constant, and so in fact you get c times b minus a. In other words, our geometric intuition, that the integral is just the area under the curve, is confirmed by a sort of mindless application of what we agreed upon at the end of last class was the definition of an integral. Okay, so this is like duh by picture. This is like I have proved it rigorously using the definition of the limit of a Riemann sum. And then there's, I think, the possibly even better way of thinking about it, which is the physics application. And this I didn't mention in the video from 5 years ago because I wasn't talking about this back then. But I do think it's really essential, which is why I'm remaking this entire video for this moment. What is the whole point of integration? The whole point of integration is to find the area under the curve, not just for fun, but to find the area under the curve to figure out how much change has occurred. And that's why the problem, we should continuously return to the problem which inspired us in the first place. The problem which inspired us in the first place is I have a velocity versus time curve, and the integral is supposed to tell me the total distance traveled. So if I have the interval from the time interval from A to B, and now I have a constant function, well then what's really going on here is I am traveling at a constant rate. Well, if I'm traveling at a constant rate c for b minus a amount of time, then of course the total distance traveled is going to be c times b minus a. So in this case, the physics also supports this kind of understanding. So if we understand the integral as the solution to a real world problem, how much distance did you travel on the time interval b minus a, going at constant rate c, as a geometry problem and as a limit of a Riemann sum. Okay, we're going to do this over and over again now for every sort of basic property of integration, and there will be times when the geometric proof is clear, but there will be times maybe when it isn't. And so okay, we're going to just do them all, and we can sort of decide what we like about them. Okay, here we go. Next, the next property. The next property is the integral from a to b of f plus g. Okay, well, already I am maybe outside of my comfort zone regarding an intuition of what this should be. And I can draw a picture. In fact, I will maybe in a minute. But perhaps this is a case where it might just be easier to do the proof. Well, yeah. Okay, so we begin. What is this? Well, it's going to be the limit, as n goes to infinity, of some Riemann sum. What is that Riemann sum? It's the Riemann sum that results from partitioning this interval from a to b up into subintervals and taking a sample point from each subinterval. Let's call it f of x sub I star. Let x sub I star be a sample point chosen from the ith subinterval, plus g of x sub I star times delta x. And there's some kind of cha. Okay, fine. Maybe brackets I use here. Okay, cha. So now what? Well, here suddenly it seems just clear to me what to do. I can distribute this delta x through these two terms, giving me two things which I sort of interpret as areas, and then those can be split up using properties of summations. So okay, if I show too many steps, it gets kind of boring. So I'll skip around a little bit because just to keep it lively. But this is the sum from I equals 1 to n of f of x sub I star delta x plus the sum of g of x sub I star delta x, and boom boom. Okay, and what's going on here? What have I actually done? What sort of algebra have I followed? This looks terrible. Okay. what algebra have I done? Is, well, okay, I just did the distributive property, boom, boom, and now I would have two things, f times delta x and g times delta x, and I'm adding up those two things n times. Well, there's no difference between adding up two things n times versus n times adding up sort of two things, or adding the first thing n times and then the second thing n times. That's all the same thing. This is from I equals 1 to m. So okay, I think you will see that by properties of summations, which are of course all finite inside the brackets, this just holds. I'm just rearranging the order in which I'm adding. But then the obvious next thing to do is to apply a limit rule. And then this becomes the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I star delta x plus the limit as n goes to infinity of the sum from I equals 1 to n of g of x sub I star delta x. Okay, and of course, what is this? This is just by definition the integral from a to b of f, and this is the integral from a to b of g. And so what I have just proved using the distributive property, properties of summations, the fact that the limit of a sum is the sum of the limits, and the definition of integration, I've just proven that the integral of the sum of two functions is just the sum of the integrals. Okay, is that sort of, was that sort of already intuitively obvious? Well, it was intuitively plausible, but I think if you try now to make a picture of this situation, it's a little bit less clear why we should sort of believe that this is true. So let me try now to draw this. And in fact, if we're going to try to understand this geometrically, then what we have to remind, what is this sort of saying geometrically? And it's possible we should have tried to do this first. But now, maybe armed with the sort of proof, we couldn't believe it, and now we can try to visualize it. Maybe that's the correct order to do this in. Okay. What is f plus g? It's the function which outputs the sum of those two functions. So what this theorem is kind of saying is, if you take the area under some arbitrary f curve and the area under some arbitrary g curve, then the sums of those two areas are the area under the f plus g curve. Alright, well, this is kind of hard to do, but I will try. Suppose I have some curve f, and perhaps that curve looks kind of like this. Okay, and then perhaps I have some curve g, and maybe the g curve looks like this. Well then, what is the f plus g curve? Well, the f plus g curve is the curve, or the function, which at every point has an output, which is the sum of the outputs of these two functions. And so if we go to try to do this, we're going to get, I have to add like that much to this or something. This is f plus g. Okay, so it's just obvious that the area under the f curve plus the area under the g curve is the area under the f plus g curve. I claim this is not obvious at all. It is very plausible, and what I'll try now to do, okay, these colors probably won't come through, but I'll try to sort of sketch in green very lightly the area under this f curve, and then in red, very lightly the area under this g curve. And okay, is it just clear that the red plus the green gives me this blue, which is the whole area under the f plus g curve? I claim, while plausible, this is not obviously true in the same kind of way that it was when we were integrating the constant function. So can we sort of make this obvious to us? Well, here we sort of lean back on the fact that an integral is really just a sum of an infinite number of rectangles, if we're going to be thinking about this geometrically. And so the way to deeply understand this is not to try to imagine all the entire shape in its sort of curviness and complexity, but instead to look at a particular rectangle on a particular subinterval. So go to the ith subinterval, go to x sub I star, and now recognize that when I plug x sub I star into f, I get a certain height, and I get a certain rectangle. And this I've tried to draw as this heavy green rectangle here. Well, then if I will plug that same x sub I star into G, I'm now going to get this other red rectangle here. And now, because I'm talking about just a single y value, I can lean on just the very definition and understanding of what function addition is. The f plus g function is just the function which outputs the sum of the f function and the sum of the g function. So yes, the rectangle, when I plug x sub I star into f plus g, I get a rectangle whose height is precisely the sum of the heights of the red and green rectangles. And so I can now say for sure that on this subinterval, the blue rectangle, the tall one under f plus g, is precisely equal to the sum of the area of the green and the area of the red rectangles. And since that's true on every subinterval, then that is in my opinion, the geometric intuition behind why the integral to sums the sum of the integrals. Okay. Yeah. As promised. Now, what about the physics? How can I sort of understand this as a physics problem? Well, okay, this I think is kind of deep. If this is my, let's just continuing to return to the same example, if this is my velocity versus time curve, then I want to interpret the integral as the distance traveled. Well, if I'm going to be integrating rates, then I need to think of some reason why you would ever have a velocity and a different velocity, and to be constructing a new velocity which was the sum of those two velocities. And a good example is sort of relative motion. So I'll just say this out loud instead of writing this down. Let f be the velocity of some train. So let f be a train, or let there be a train which is moving along the ground, and let f be the speed of that train, or the velocity of that train. Well, if f is the velocity of that train, then if a and b are times, then the integral from a to b of f is the total distance that that train travels during that time interval. Okay. Let g be the speed of someone walking on that train. So someone now is on that train and is walking sort of forward at a reasonable pace of, like, a couple miles an hour or something, along the train in the same direction that the train is moving, but on the train. Well, it's natural to describe that person's velocity with respect to the train, not to the ground. So then the integral, if that's what g is, the rate the person is walking relative to the train, then the integral from a to b now would be the distance that that person travels during that time interval, but relative to the train. Well, if you add the velocity of the train relative to the ground and the velocity of the person walking on the train relative to the train, then in fact you get the velocity of the person relative to the ground. And what this is sort of saying is that the distance the train travels plus the distance the person travels, the distance the train travels relative to the ground, plus the distance the person travels relative to the train, is the distance that the person travels relative to the ground. I think that's the sort of physics interpretation of this property of integration. Okay, more. Here is another one. This one also very plausible, but okay, let's just do it. What is the integral from a to b of c times a function? Okay, well at this point you might just be thinking, okay, come on, all these things are just doing exactly what you think, and isn't this just c times the integral from a to b of that function? And I don't really know, because I'm alone in a room right now, whether you're thinking about this algebraically, you're thinking about physics, you're thinking about geometry, or all of them, or most of them, and I don't actually even know, for even my own self, which of these is more sort of intuitive. Well, okay, perhaps I'll just begin with the definition. It's the limit as n goes to infinity of the sum from I equals 1 to n of, okay, it's actually sort of kind of awkward because this is in some sense, yeah, I'm basically defining a whole function now whose output is c times the f function. But anyway, when I plug a sample point into that function, I get c times f of x sub I star is the output times delta x. So that's just what an integral is. It's the limit of a Riemann sum, and a Riemann sum is just the sum of a bunch of products of functions and widths of intervals. Okay, but of course, maybe everyone just sees kind of immediately that this c is a constant, so you can pull it out of the summation by properties of summations. That's actually just really, it's just the distributive property is what it is. And then also just out of the limit, because we have a limit law for that. So this becomes c times the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I star delta x. And this is just the integral from a to b. And so we've proven our theorem. Okay, so in that case it was kind of easy, and I guess I would argue that it's actually my sort of algebraic intuition that this constant doesn't matter because integrals are really just sums. That's just really what they are. Integrals are really just infinite sums that makes this sort of obvious that I can just pull it out. Okay, what's the geometric interpretation? Hopefully we're getting maybe a little better at this now or something. What's the geometric interpretation? Well, it's now that I have some function, I guess again it's a velocity. No, I don't want to talk about physics yet. I just want to talk about geometry. The geometry of this, that the integral from a to b of c times f is just c times the integral from a to b of f, would be, well, okay, I need some sort of generic function, f, and I need to talk about what is the integral from a to b of that. Well, it's just the area under this curve. So, okay. And now, what does it mean to multiply some function by some constant? Well, it's like a scaling operation, right? C times f is just the f function stretched out by a factor of c. And so here, let me try to make, let's see, how much will my board support? Maybe c is like 3 or something. If c is like 3, then this is maybe like, 3f. So the 3f function is the function which is 3 times bigger than f. In other words, you multiply every y value by 3. And that's just going to stretch the entire function vertically by a factor of 3. Let's just call it c though for, just because. But we think 3. Well, is it obvious that the area under this purple curve will be c times as much as the area under the f curve? I claim it's not totally obvious, but once you consider the problem as we did before on a subinterval by subinterval basis, it becomes a lot more clear. So if you split this up into subintervals and you go to x sub I star and you look at the rectangle drawn on the I subinterval, then you see that its height is, well, it's f of x sub I star. And then, by the very definition of what it means to multiply a function by a constant, when I plug that same number x sub I star into the c times f function, it will be c times its height. And so I can say that this rectangle will be precisely c times taller than the green one, and so its area will be c times as much. And so on this subinterval, the purple rectangle has c times as much area as the green one, but that holds for every subinterval, and so it holds for the integral overall. Okay, so that's the geometry, which I think was, well, the picture is plausible, but the argument is maybe requires some care. All right, and then finally, I don't think you really maybe understand this until you can apply it to some kind of physics problem. So if this is a velocity versus time curve, how can we sort of tell this story now? Someone, I think, came up with this example in some previous year. Okay, let f be some person who is walking. Let that be their normal walking speed. So if someone is walking at some normal walking speed f over some time interval ab, then the integral from a to b of f will be the distance that person travels. But if now suddenly they have received some kind of boost by factor c, so maybe c is like back to being 3 or something. Suppose what they now have done is put on stilts, and those stilts are increasing their stride by a factor of c. So though they're walking, normally, so to speak, at their normal rate, their legs are 3 times as long somehow, and so with every normal step on the stilts, they cover 3 times as much distance, and so their velocity is 3 times greater. Well, okay, I'm sort of saying it as if it's obvious, because it is. If your velocity in every single moment is 3 times bigger than your normal velocity, then of course your total distance traveled is going to be 3 times as great. And that's maybe the real way of understanding this. Okay, good. I think I've sort of proven my point that there's maybe more to these than seem initially. Let's just do the last couple. What are the last couple? Here's one that's extremely obvious, but actually maybe hard to prove. So the integral from a to c of f plus the integral from c to b of f. What is this? Well, if you make a picture of this, it's just very clear. If this is a, and this is b, and this is c, if we take the integral from a to b under this f function, and then we sort of just continue, this is also f, from b to c, then, okay, here you have some area, here you have some more area, and what happens when you add these up? You just get the total area from a to c. So this is a property of integrals, that the integral from a to c plus the integral from c to b is the integral from a to b. And I think geometrically it's completely clear, and I think the physics is also clear. If you have, once again, some velocity versus time curve, and you take the integral from a to c plus c to b is a to b, there we go, fixed. Then this green is the distance traveled on the time interval ac, and this red is the distance traveled on the time interval from c to b. And if you add up these distances, then you just get the total distance traveled from a to b. So, however, if you try to do the proof using the Riemann sum, it's kind of hard somehow. And in fact, what's going on here is that I have some sort of partition of the interval AC up into tiny subintervals, and then I have some perhaps